So, good afternoon, everyone. I know this session has been planned just after the lunch hours, but we promise we'll try to make it interesting till the end. It's truly an honor to be here at KubeCon India. This is going to be my first talk at such a huge event, and to be in the same room amongst such an inspiring community of innovators, technologists, and open source enthusiasts is truly overwhelming. My name is Shivani, and I welcome you all to this session of extensive scalability testing on ArgoCD for 30,000 plus applications at Expedia Group. Today, we are excited to take you through our journey, which is a story of challenges, solutions, and of course, innovations. We hope to share some valuable insights with you all, some lessons learned, and some good practices that you guys can take back to your own teams and your own projects. Thank you again for joining us, and we look forward to an engaging session with you. Before we go into the technical deep dive about our scalability testing initiative, let's first get ourselves introduced. Hi again, my name is Shivani Mehrotra. I'm working as a software development engineer at Expedia Group. It's been 1.5 years for me now at EG, and a total of 5 years for me in the industry. I'm accompanied by an extremely very talented speaker, Mohit.
Hello everyone, my name is Mohit, and I've been working with Coforge for the last 7 years. And I've been associated with Expedia Group for the last 1.5 years. And yes, we are very much excited to present a talk on a very significant initiative of ours before such a huge audience. So yeah, that's me. Over to you, Shivani.
That's true, Mohit. This is significant, not only because our team worked on this, but because it benefits us, and it could benefit your organizations as well in many, many ways. We are excited to walk you through our journey and share some key insights with you all that we gained while building and scaling our platform. So we'll start by discussing the migration journey from KubeFed to ArgoCD and the challenges we overcame during this process. Next, we'll delve into the design and implementation of the scalability testing platform that we created, which ensures our platform's performance at scale. Here, we'll also highlight the ways our work benefits the broader ecosystem. We'll also discuss the scalability testing strengths, how this scalability testing strengthens our platform's resilience and helps us achieve high availability. We'll also provide insights into the fine-tuned configurations that were optimal for our setup. Finally, we'll open the floor to your questions, and we look forward to have an engaging session. We hope this session provides some practical insights and sparks some great ideas for your own journey. So let's get started with an overview of our journey from migrating from KubeFed to ArgoCD. Before going into that, let me first introduce you to RCP. RCP is Runtime Compute Platform. Runtime is the name of our team as well. And RCP is an in-house built platform at Expedia Group, which is a multi-tenant Kubernetes-based container orchestration platform. RCP operates at an incredible scale, ranging from hundreds to thousands of clusters. This scale highlights RCP's ability to serve as a reliable and efficient backbone for our business-critical services. As you can see on the slides, here's a glimpse of some of the tools that we use in our setup. So yes, the migration part. Originally, RCP leveraged the KubeFed architecture to manage the clusters and their applications. It was the suitable choice at that given point of time. But however, when KubeFed got deprecated, it became clear for us that we had to adopt a more sustainable, modern, and a feature-rich solution to meet our platform's evolving demands. And that's why this led us to ArgoCD, a robust GitOps tool that allows us to manage our Kubernetes resources declaratively. ArgoCD provides capabilities like multi-cluster application synchronization, automated rollbacks, version control integration, and many more, which actually fit our needs. So the primary motivation behind the scalability testing actually was rooted in this migration. Because with this transition, it became crucial for us to understand how our platform would behave under varying workloads and certain different configurations. So our major focus was to test workload distribution across the platform to ensure even and efficient utilization. We also wanted to experiment with certain different ArgoCD tunable parameters to identify the most optimal settings for our setup. We wanted to prepare our platform for future workload demands. Ultimately, this exercise wasn't just about migrating to ArgoCD. It was to understand and proactively validate that ArgoCD could meet our current platforms and future requirements. Let's take an overview of how we have set up our platform for performing extensive scalability testing. So if you look at the slides, we created one ArgoCD control plane that acted as the master. Attached to this control plane is an artifactory, which actually serves as a central hub for storing our application Helm charts. So it became quite easy, and it allowed seamless pulling of application Helm charts during the deployments. To also streamline the deployment process, we wrote an automation in Go. So how this script helped us? This script enabled dynamic deployment of applications to the target clusters that were attached to this control plane. It also provided the flexibility to define the number and the types of applications we wanted to deploy on the target clusters. This setup allowed us to test ArgoCD's scalability under real-world conditions, ensuring its reliability and maintaining the performance when managing a large number of applications across multiple clusters. So you must be wondering, we have a lot of target clusters, we have vclusters as well. So yes, our control plane was actually connected to a certain number of target clusters, and each target cluster was hosting a number of virtual clusters. To highlight the previous diagram back again, so yes, some key points is that we created one ArgoCD control plane, that was the master. We attached 10 target clusters to this control plane, and each of the target cluster was actually hosting 11 virtual clusters, which we spin up using the vcluster tool. I'm sure most of you might be aware of it, but still, the vclusters allows us to mimic real-world cluster setups. It enables to analyze scalability across diverse configurations. We also created a custom automation in Go, which actually was creating application sets on the control plane. So now this application set was responsible for creating applications on all the target clusters that were attached to this master. And the application sets were creating nothing but simple Helm-based applications. So another important thing to highlight, so we created 3 different sizes of applications, ranging from small, mid, and large. So we wanted to cater some real-world production applications where maybe some of your applications might be running heavy workloads, and some might be some simple Kubernetes resources. So yes, small applications were actually creating somewhere around 10 Kubernetes resources. Middle-sized applications were creating 15 resources, and large-scale applications were actually creating 25+ Kubernetes resources. This could include Kubernetes jobs and CRDs, etc. Quickly, let's take a look at how we can benefit our ecosystem. So our journey to adopting GitOps at Expedia Group was not just about switching the tools. It was about making sure that our new system could handle our large-scale needs. So yes, with this scalability testing, it revealed key tunable parameters of the ArgoCD controller and several other components, enabling efficient management of a huge number of applications before migrating them to production. We conducted scalability testing on 3 times the number of applications we currently have in our production environment. So this ensured that we are prepared for future load increases. Utilizing vclusters, yes, we optimized costs associated with this scalability testing. This approach showcased how we can effectively manage the resources and offer a cost-efficient model, which other organizations can also adopt. Through this talk, for an example, we are sharing our scalability testing journey, which can help the community understand the practical aspects of scaling ArgoCD. And this contribution is invaluable for teams who are seeking to improve their GitOps practices or to implement the same. We conducted these tests using applications that are identical to those that we have in our production environment. So yes, we tried to simulate the real-world production applications. Enough with the theories. Here comes the exciting part now, where we'll get started with discussing how we have tested and what kind of test cases we designed. So handing over to Mohit.
Thank you, Shivani. Thank you for the brief introduction. So yeah, let's get started with the scalability design. So yes, now we will go through the whole scalability testing design. The test cases that we have designed that are more towards the Expedia Group application distribution. We wanted to design our test case to keep in mind the number of volume of applications according to our production environment. So we started with some ArgoCD tunable parameters like sharding algorithm, shards, repo server controller settings, status processor, operation processor, and yes, with some testable parameters like CPU and memory of application controller, repo server controller, and yes, we wanted to know the exact value of these parameters, which will be suitable for our environment before migrating our production workload to ArgoCD. So we started with our scalability test cases with the default values of ArgoCD components, and we performed several iterations of these testing until we found the optimal settings for ArgoCD which was suitable for our environment. Further, I'll be discussing about 4 test cases here, including deployment of 13,000 applications progressively all at once, and deploying 30,000 applications in a similar manner, and yes, final test case will be more inclined toward resiliency. So yeah, this was the first test case which we conducted during our scalability testings. We have deployed approximately 120 medium size of applications across 110 virtual target clusters. These applications were deployed progressively, where we have deployed 1,100 applications with a 2.5-minute interval spread over 12 iterations, as you can see in the right side, where we have mentioned about the distribution of the applications. So yes, let's take a look at the parameters which we have chosen for the scalability and their relevance on scalability. Repo server parallelism limit. We started with a parallelism limit of 250 in the repo server that determines how many manifest generations can run concurrently. We have kept shards since we are testing with the 100 of 10 of target cluster, so that each shards has a 10 to 11 virtual target clusters to manage. Status processor and operation processor. By default, ArgoCD has a status processor and operation processor values set to 20 and 10 respectively. Status processor uses a queue to manage application status updates. The controller status processor settings controls the number of threads that checks and updates the status of applications. Similarly, we have operation processor settings that controls the number of threads used to execute operation like syncing, rollbacking, and pruning resources. This test case has been performed in 3 iterations, where we have changed status processor and operation processor value in each iteration, where in the first iteration we have kept 100 and 200, in the second iteration of this test we have kept 200 and 300, and in the third iteration we have kept 300 and 420. Now the final settings which we have: client QPS and client burst. These settings control the rate of API request that ArgoCD sends to the Kubernetes API server, and the values which we have considered here are 50/100 in the first scalability test case. So yeah, here are the observations which we have concluded from some of the important metrics of ArgoCD controller. For the first test case, the status processor and operation processor was set to 100 and 200, in the second 200 and 300, and the third 300 and 420. So the total time to sync 13,000 applications was similar, almost similar across 3 configurations, averaging around 40 minutes. When we have compared CPU metrics for all the 3 iterations of this test, there was nothing major observed in the first 2 iterations, but in the third iteration of the test, we see some spike in CPU for one of the shard reaching its CPU limit. So that was the observation which we have observed in CPU. The another important metrics which we have included in our scalability testing was app reconciliation queue and app operation processing queue. App reconciliation queue, a queue that handles the periodic reconciliation of application to ensure the live state matches the desired state. Similarly, we have app operation processing queue, a queue that handles user-triggered or automated operation on applications such as syncing, rollbacking, or pruning of resources. During the application deployment, in both the metrics, where some of the shards spiked for a very short span of time, but that got cleared without any noticeable impact on the performance of the application controller. So yeah, that was the observation which we have observed in app reconciliation queue and app operation processing queue. So the overall observation which we have concluded from this test, in the third iteration, where both the status processor and operation processors were higher, we observed a significant reduction in sync time across all 12 iterations. We also did some resiliency testing in this test as well, where we have restarted application controller and repo server. However, there were no significant changes in the sync process or the health status of the application, showing that ArgoCD is resilient to these types of disruption. So the conclusion which we have observed from this testing, that it helped us to identify the optimal configuration of the ArgoCD controller. We have implemented these settings in subsequent test cases to further evaluate the performance of ArgoCD scalability. So yeah, that was the first test case, and we have observed our optimal settings till now. Moving to the next test case. In this scalability testing, we have deployed mixed set of applications. Mixed set of applications means that we have included small size of application, medium size of applications, and the large size of application, which Shivani has already told you about. That depends upon the number of resources. So the key factor in this test was the application distribution. As in ArgoCD, each shard manages its own set of target clusters. The performance and the resource consumption of each shards are directly impacted by the number and the type of the applications on its target clusters. The distribution was designed to observe the behavior of individual shards under different application loads. So you must be wondering what has been changed, because the application distribution in both the two iterations of this test we have kept same. So yeah. Status processor and operation processor we have kept at 420 and 300, which has been derived from the last test case where we have seen better performance. Reconciliation time we have kept at 240 seconds, and now in this test case we have changed client QPS in the first iteration, and then in second iteration we have kept at 100 and 200. We wanted to check if there has been effect of client QPS and client burst on the performance of the ArgoCD controller. So yes, the observation which we have concluded from this test, that in the first iteration, the total time to sync 12,000 application was around 24 minutes. In the second iteration, the total time to sync application was 21 minutes, which was slightly faster than the first iteration, where we have kept client QPS and client burst second 100 and 200. When comparing the graph of the CPU metrics in both the iteration of the test, we have seen some CPU spikes in a specific shard 3 in the second iteration. However, this was due to the fact that the target cluster with the highest number of applications were assigned to this shard, resulting in the observed CPU spikes, and that was expected. Another important metrics which we have observed, app reconciliation queue and app operation processing queue from this test. However, no significant behavior was observed in the application reconciliation queue or the app operation processing queue. However, a small queue did form in the second iteration of app operation processing queue, but that was cleared without any noticeable impact on the performance of application controller. Moving to the conclusion for this test, the past sync time achieved during testing was 21 minutes with the client QPS set to 100 and burst QPS set to 200. We also did some resiliency testing as well in this case by deleting application controller ports. However, these actions did not cause any noticeable impact on the sharding or the cluster resource distribution. In this test, we have included applications with jobs as part of their resources, which were created and recreated during each reconciliation cycle. However, this behavior is already addressed by the ArgoCD using hooks, so there were no major concerns. As part of this testing, we did another testing by redeploying all 12,000 applications by changing port labels, invalidating the Redis cache, and recycling of the running ports of the application controller and the repo server. We observed that the work queue depth increased for all shards, and there was a noticeable rise in CPU and memory consumption compared to the when applications were initially deployed. So yeah, that was the observation which we have observed during this testing. Now here comes the third test, where we have deployed mixed set of application by increasing our loads 3 times. This test has been performed in 2 iterations where distribution of application is different. In the first iteration, we have deployed 330 mixed set of application on each 110 virtual clusters, resulting in 36,000 applications. The sharding algorithm we have used in the first iteration was round robin. In the second iteration, we have deployed 165 mixed set of application in 100 of the clusters, as you can see in the second diagram. That has been deployed in each of 100 target clusters. But for some of the few target cluster, we have deployed some high number of applications where we have deployed very large applications. Like, as you can see in the table, we have deployed 1,200, 2,400, 2,000 applications on a single virtual target clusters. So we simulated a scenario similar to our production workload where some target clusters are running a high number of applications. So here in the second iterations, we have deployed around 32,000 applications. We used a combination of manual sharding and round robin sharding. The 9 target clusters with a high number of applications count were manually assigned to specific shard, ensuring that not all high volume clusters were attached to the same shard. These were the resources which we have kept for controller like repo server and application controller. Status processor and the operation processor we kept at 300 and 420, which has been taken from the previous test where we observed the better performance. The client QPS and client burst has been kept at 100 and 200, which has also been taken from the previous test cases. Now come the observation part from this test. In the first iteration, all application got synced in 72 minutes, but in the second iteration, syncing of all application took 100 minutes, which is longer compared to the first iteration. If I talk about the CPU performance, there was no significant difference in the CPU performance of the ArgoCD application controller between the two test iterations. This suggests that the distribution of application did not have a notable impact on CPU performance when we have, in the second iteration, when we have manual plus round robin. App reconciliation queue and app operation processing queue. So yeah, by testing this round robin and manual plus round robin, if I talk about the app reconciliation queue, a small queue also formed in the application processing queue during the second iteration, and also this time this affected the sync time as well. During this iteration, we noticed a significant sync time difference of 28 minutes. This delay was linked to a specific shard 1, which was handling target cluster with a high application load. The queue formation on this shard contributed to the increased sync time, which we have observed. We have also included metrics from Kubernetes API server, especially from the ArgoCD control plane Kubernetes server. We aim to check if there was an increase in the Kubernetes API server latency, however the latency remained within the acceptable range with no significant concern observed. We also monitored the Kube server latency for all target clusters, and once again, no major issues were observed. So yeah, the conclusion that the combination of manual sharding and the round robin sharding work well for our setup where certain clusters handle a heavy load while others manage a normal load. We were observed an increase in sync time when the application distribution varied across clusters, particularly when clusters were manually sharded. Now the scalability test 4, which is something not related to scalability, but more toward resiliency. The final test, which we have conducted, here we have removed some of target cluster after deploying applications. In this test case, we have deployed 16,000 applications across all 110 virtual target clusters, consisting of a mixed set of applications. When we deleted 4 target clusters, where a total of 540 applications were deployed, after deleting the cluster, virtual target clusters from the ArgoCD control plane, all applications deployed on this cluster showed a sync status of unknown and a health status of unknown. Upon deletion of this cluster, ArgoCD began reshuffling the remaining cluster across all shards that was expected in round robin. We then redeployed the application sets targeting 20 virtual target clusters, which included the 4 clusters that had been deleted previously. The observation which we have noted from this test that the new applications were only created after ArgoCD had cleared the unknown status of the previously deployed applications. So this was the observation which we have observed during this test. So that would be all from my side for the testing which we have performed. Now handing over to Shivani for taking the talk forward.
Thank you so much, Mohit. I hope this technical deep dive of the test cases that we designed. I know there was a time crunch, so we discussed just a few of the test cases, but please be posted. We'll try to come up with a blog soon, including a lot of other test cases that we did. So I hope this knowledge could help you guys to understand the key aspects of the test cases design and to how to understand their results, etc. So let me take you through some optimal settings that we observed that actually worked for our setup at EG. You guys can take a reference when in future or maybe currently if you're trying to perform such scalability testing. I would like to highlight that these values worked well for our setup, the number of clusters that we created at such a huge scale. So these settings might vary from organization to organization, infra to infra. So yes, I won't be repeating the same values again. I think you guys have heard it a lot of times in the previous test cases. But yeah, so these were some of the application controller optimal settings that worked well for us. And these are some of the ArgoCD repo server settings that worked well for us. So also, please take a reference. But yeah, these settings might vary for your organizations and your setups. Thank you so much. The floor is now open for questions. Please connect with us on LinkedIn as well. Thank you.
Thank you. Okay.
Yeah.
You mentioned something regarding that the application states would come back up, but each time it would take a bit more time. And you say that it's not a big deal. Like, what kind of more time is it, and why do you think it's not a problem?
Actually, when we started with some 13,000 applications. So that time we have deployed a similar kind of application on each and every target clusters, and we all know that distribution of applications might differ on each and every target clusters, and ArgoCD performs differently, because if a target cluster with a high number of volume applications has been attached to some shards, and some of the shards where low number of applications are running, target cluster attached to other shards, so there might be difference in sync time, and there might be difference in the resource consumption as well. So yeah, that is something which we wanted to test, because in our organization, application distribution on every cluster is different, where some of the clusters are running high number of applications and some of the clusters are running very low number of applications. So that's why we came up with this solution like manual sharding and round robin, where we have fixed some target clusters with manual shard. We have assigned manual shard to those clusters so that high number of application clusters did not land up in the same shard, because that will be a problem of resource consumption. Because if suppose shard 0 has been all the target cluster where high number of application got attached to shard 0, if we did not use manual shard, then there will be a resource consumption problem in ArgoCD controller, right? So yeah. And sync time vary as per the application as well.
Yeah, so my question was, how do you tackle the problem of shared resource warning? Because basically, if sometimes developers misconfigure like PDBs and or other Azure keyword secrets, they put the same name to two dashboards. So the ArgoCD is stuck in the loop of, for example, one application syncs the resource, changes some labels, and then second application becomes out of sync. So it starts to sync, then it becomes out of sync. So if there are 2 to 3 dashboards like that, it floods our refresh queue. So do you have some validation in place, or what can you suggest for that shared resource warning should be prevented?
Shared resource warning. I didn't get.
Yeah, so basically, if two resources, like for example, say there is a Azure keyword secret with some name.
So yeah, we have like a ignore differences in ArgoCD.
Yeah?
Ignore differences.
Okay, ignore differences.
Right.
Also, we can set up some Kyverno rules and policies to, avoid that kind of a situation. We are using Kyverno here.
Okay, okay.
Yeah.
Thank you.
Any other questions? Then thank you so much, everyone,
Thank you
for
so
being a
much.
great audience.